Chapter 7, Basic Aeronautics and Aerodynamics, the Realm of Flight. So we're going to talk about all the things it takes to actually fly and keep an airplane in the air and stuff, and that's what this presentation is going to be about. So as we start here, we're going to talk about the air and the properties of the air. And one of the things we're going to start with, and some of these terminologies you've familiar with, is air pressure. You've heard of that. You can watch any weather reports and stuff like that. They talk about the air pressure and stuff like that. So in air pressure, the higher you go in the atmosphere, the less pressure there is. So when you stop and think about it, the higher you go, the less air there is above you pushing down. Okay, if you think about it, similar to blankets on a bed type of thing, is if you have a lot of blankets on, it's heavier. Okay, if you have fewer, take a couple blankets off, it's lighter on top of you. So that's kind of how pressure works. The higher you are, the less air pressure. The lower you are, the more air pressure, the more is above you. So what that indicates is that the pressure at sea level is considered to be 14.7 pounds per square inch. So 1 square inch of space has 14.7 pounds pushing down in that square inch. So when you stop and think about that, let's just look at New Prague. Okay, excuse me. New Prague is 988 feet above sea level. Okay, and so when you equate that out to if it's at sea level, it's 14.7 pounds. So we're higher up, so it's going to be less than 14.7 pounds. And we are actually at 14.18. It's not a lot less, but it's 14.18. So we're closer to 14 pounds than the sea level, which is closer to 15 pounds. Okay, but now let's look at it the other way. Let's go, that we're kind of, like I said, 988 feet. Let's look at New Orleans. Okay, New Orleans, remember back when the Katrina went through and all the talk about how the problem with New Orleans is it's at sea level. Well, it is. It's 15 feet above sea level. Okay, so at 15 feet above sea level, its PSI is 14.7 pounds per square inch. Makes sense. You're right in there. I mean, it's probably, if you take the numbers out a lot farther, it's probably like 14.66 or 6999993 or something like that. But it's at that level. So you have the full weight of the atmosphere above you in New Orleans. And we go to the opposite end, or one of the opposite ends in the United States. If you go to Denver, Denver itself is actually 5,280 feet above sea level, which is a mile. Okay, that's why they call it the Mile High City. And when it's 5,280 feet above sea level, their PSI is 12.10. So there's less air. You get 2 pounds less air. That's why if you watch a football game and they talk about the air being thinner, it's not thinner. It's just there's less of it pushing down on you. But they talk about the air being thinner. You'll see the players wearing, or after long runs and stuff like that, you'll see them with oxygen masks on and stuff like that. The other thing they will talk about is it's easier to kick a ball farther in Denver than it would be to kick a ball in New Orleans, because there's less pressure pushing the ball down faster, so the ball can fly higher. So that is kind of how pressure works in pressure in the atmosphere. And think about when you're flying, the higher you fly, the less pressure, the less weight on the plane pushing down. You still have gravity pulling on you, but the less weight above is also pushing down on you. The next one, temperature. Temperature is a measurement of energy within a gas. Okay, so the hotter the air, the more energy it has. So the best time to actually fly, if you were ever to go to flying and stuff like that, especially the smaller airplanes, but the best time to fly is actually in the winter time, because the air has less energy in it. So the air isn't moving around. You don't hit these thermals and stuff like that, these things that bounce the plane around. You'll find more turbulence when you fly a plane in the summer than you would if you flew a plane in the winter. So that's what we say about there's more energy. There's more air movement going on because of the temperature. So the higher the temperature, the more energy, the more movement there is that the plane is going to have in the air. Keep in mind also, air temperature decreases at a rate of about 3.5 degrees per every 1,000 feet in altitude increase. So let's just take Denver for example. You'd go to the foot of, you go down to, if you were able to go down to sea level in Denver area, it may be 30 degrees at sea level, and then as you go up, it's going to just keep dropping 3.5 degrees every time you go up. So 26.5 degrees for 1,000 feet, and then another 1,000 feet, it's going to be what, 22 degrees. So 20 or 20, whatever. And so it's going to just keep increasing, okay, or decreasing as you go up. When you get to about 38,000 feet, then the temperature doesn't change that drastically. It may change very little above 38,000 feet. Part of the reason is there's not a lot of that air pressure. There's not a lot of air up there, so there's nothing to warm. Okay, there's nothing to warm, so, or cool in that case. So pressure and temperature, obviously two things that you see a lot in weather reports and things like that, have a big effect on aviation because of how you can fly and how the plane reacts in that type of situation. Another thing is density. Density is essentially how many molecules are squeezed into a given volume. Okay, so when you stop and think about how dense is the air, there's some days you get up and you can feel that it just seems heavy. It seems really dense, because keep in mind, air is compressible. You can squeeze air. Okay, you can squeeze air, so it's compressible. In our 7th grade class, we used, for our CO2 dragsters, we use those little compressed canisters. Okay, you just pump air into it. You compress the air into there, and then we pop that little hole in there. It just comes shooting out. Air compressor is the same thing. It takes the air that is not compressed, and it takes it and puts it in a tank and just compresses it and compresses it, compresses it, packs it in as tight as it can get in there. Okay, so there's density in the air that has an effect on how an airplane flies. Okay. Laminar flow. Okay. Laminar flow is the flow pattern of air around an object. Okay, and you want your flow pattern, I mean, it would make sense to be really, really smooth. Okay. You really want that flow pattern just to flow really nice and smoothly. The rougher it flows, the harder it is for an airplane to stay in the air. Okay, it's called turbulent. Okay, and that's non-desirable stuff. You don't want a turbulent air, because that's going to affect keeping the airplane aloft, and with that lift that we talked about in a few PowerPoints ago. Okay, and keep in mind, most airfoils experience both flow patterns, because as of right now, you can't get a perfect flow pattern. Okay, you can't get that perfectly smooth. You're going to have smooth, but you're going to have some turbulent. Coming off the back of the wing, you're going to have some turbulence coming off the back of the wing, because you have two air masses, the air that flows over the wing and the air that flows under the wing, hitting each other. And we'll talk about that a little bit later. But there's going to be turbulence when that air meets again. There's actually going to be little turbulence when the air hits the front or the leading edge of that wing also, because you're smacking it against something. It's going to roll. It's going to become turbulent. But as it flows over the wing, it smooths itself out, and then thus allows the airplane to lift. So this is laminar flow. Okay? We also talk about viscosity. Viscosity is a fluid's resistance to flow. Okay, and so as you keep in mind, air is a fluid. Okay, and the greater the resistance, the more viscous the fluid, so the thicker the fluid would be. Okay, so like I said, air is a fluid, and So what you want is you want a nice smooth flow. And I have a video here. It's a fairly short video that talks about the viscosity and how viscosity works and stuff like that. So we're going to take a look at this video.
Viscosity is a measure of a fluid's resistance to flow. This means that some fluids will flow faster than others. If a fluid is less viscous, it is more able to flow. Here we see that a fluid being dropped from above is easily flowing over the sides of the pan. This means that there is less resistance to flow. Due to this, more of the fluid is able to flow over the sides of the pan. If a fluid is more viscous, it is less able to flow. Here we see that the fluid is not flowing over the high sides of the pan very much. This means that there is more resistance to the fluid's flow, and less fluid will flow over the sides. Now let's head to the kitchen to see what low and high viscosity fluids actually look like. Here we have two glasses, one containing milk, the other containing honey. As bubbles are blown in the glasses, watch carefully and look at the movement of the bubbles. As you can see, the bubbles in the milk flow up and pop at the surface quite fast, whereas the bubbles in the honey flow up much slower and look goopy. But why is there a difference in the movement of bubbles? Viscosity, of course. We know that either milk or honey is more viscous, but which is? Since the bubbles move much more slowly through honey than milk, we can say that honey is better at resisting flow than milk is. Therefore, honey is more viscous than milk. But what happened here on the molecular level? Intermolecular forces are what affect viscosity. If a fluid is less viscous, like milk, there will be weak intermolecular forces and fewer bonds. If a fluid is more viscous, like honey, there will be strong intermolecular forces and more bonds. Now think about what is happening on the molecular level as we move a straw through our glasses of milk and honey. Since milk has low viscosity, I can overcome the intermolecular forces and move the straw around easily. Since honey has high viscosity, I cannot overcome the intermolecular forces as easily, so I feel a greater resistance as I move the straw around. Now let's look at a type of viscosity called kinematic viscosity. This is a fluid's resistance to flow under the influence of gravity. Think of it as pouring water from a bottle versus pouring maple syrup from a bottle. What's the difference when you pour these? Now let's head back to the kitchen and investigate kinematic viscosity of milk and honey. Here we have drops of milk and honey on a pan. What will happen when I lift the top of the pan? Due to the low kinematic viscosity of milk, the milk races down the pan. Finally, honey starts moving down the pan. Its slow movement is due to its high kinematic viscosity. Now here's an interesting thought. What happens to the viscosity of a fluid if it's at a higher temperature? Try to identify which glass of honey is at a higher temperature. Here's a hint. High temperatures cause molecules to speed up in liquids, which causes a decrease in intermolecular forces. Do you remember what weak intermolecular forces mean in terms of viscosity? Which glass of honey was at a higher temperature? the honey on the left has low viscosity. It moves like milk as the straw swirls around. As this honey was heated up in the microwave, the temperature increase caused the intermolecular forces to decrease. This results in a low viscosity liquid. Comparing the movement of the high temperature honey to the room temperature honey, it is clear that the temperature has a great impact on viscosity. Viscosity is an important property of fluids in the chemical and chemical engineering worlds. But as you go about your daily life, think about the viscosity of fluids you encounter. Is the water flowing out of the kitchen sink a high or low viscosity fluid? What about the syrup you put on your pancakes?
So that was the video about viscosity. Keeping in mind it talked about fluids with milk and honey. But remember what we said, the air is actually a fluid. So that's why that was important. So you kind of understand the viscosity difference and so that. And you usually hear that terminology used with engine oil that would go in cars, more of a higher viscosity engine oil versus a lower viscosity engine oil, and how well it's going to flow through the engine. The slower it flows through, the harder the engine is going to have to work. The faster it flows through, the less the engine is going to have to work. Okay, so let's continue on with composition and properties of air. The speed of sound in air, let's talk about that, because that's one thing that a lot of people are always referring to as the speed of sound. Keep in mind that it's a disturbance that produces sound causes a reaction that is transmitted in all directions. So you have a sound at a center point. The sound, or I should say a disturbance at a center point. The sound is going to radiate in all directions away from it. Now, when you think of it as two-dimensionally, if I pounded on the table where my fist hits the table, that's where the disturbance is caused, and the sound is going to radiate 360 degrees out along that surface of the table. But sound doesn't just go in 2 dimensions. Sound actually flows in 3 dimensions, so it will not only flow 360 degrees from or level with the table, but it will flow 360 degrees in all directions, above, below, everywhere from that disturbance. So understand, sound is like a ball that is expanding out. Okay, sound is like a ball that is expanding out. So small local pressure changes that appear to radiate outward waves, and that's kind of what we're talking about. So there's a gentleman by the name of Ernest Mach, and you may recognize the last name, but Ernest Mach, he was the person that determined the correct mathematical value for the speed of sound. And with all the math, we ain't going to go into the math or anything like that, but just understand that he determined that approximately 761 miles per hour at about 59 degrees Fahrenheit is the speed of sound. And they use, that's the rough estimate. That's basically when everybody talks about the speed of sound, they're talking about 761 miles an hour, right around 760 miles an hour. And just to show you that it's 692 miles per hour at 30 degrees Fahrenheit. So you can get to the speed of sound faster at a lower temperature. Okay, so the speed of sound is one of those things, and it's just like I remember growing up, and there was a neighbor that was probably about a block and a half away, and I could see his house, and he was building a shed. And I'm sitting in my yard, and I can see him building a shed, and he's hammering, and I can see the hammer hit the nail, or I can see his hammer swing to hit the nail, but I don't hear, as soon as I see the hammer hit the board or wherever he's hitting, I don't hear the sound. It takes a fraction of a second for that sound to get back to me. Okay, it's not like light. Light is much, much faster than sound. Okay, so it takes that fraction of a second to get back to you, and at 761 miles per hour on a normal day, okay, it had taken just that little bit of a second where I can visually see it, which is my light. I can visually see it happen which is light travel, but I can't hear it happen the exact same time because there is a difference in speeds between light and sound. So I just kind of, you've seen stuff like that where you can see something happen, but you don't hear it till fractions of a second later. Okay. Well, so Ernest Mach came up with this mathematical formula and figured this out. And as the airplanes were going faster, they were trying to go, can we go that fast? Can we go the speed of sound? Okay. We at this point already knew that a bullet can go the speed of sound. Okay. We already knew a bullet could. So it's now, can we go the speed of sound? And one of the things that was always being talked about was, what's going to happen when we get to that point at 761 miles per hour? I mean, we're close at, we were really close at, getting to this speed, but they talked about it as like a sound barrier. Okay. And they didn't know what was going to happen. If you hit this, is it kind of like hitting a wall, and all of a sudden it's going to just like disintegrate your airplane and anything that's along with it and stuff like that. So they were looking at trying to achieve this sound barrier. Okay. So they believed the speed of sound could not be achieved. Okay. They believed that was really too fast to go. Okay. Well, Bell Laboratories, in association with the predecessor to NASA, created a airplane, so to speak, that was called the Bell X-1. The Bell X-1, because we knew that a bullet could break the speed of sound, the Bell X-1 was shaped very similarly to a bullet. Okay, and so they were attempting to break the sound barrier with this Bell X-1. And what they did is, in order for it to be a conservative of energy, they took this airplane, and they had really short, stubby wings, and they took this airplane and they hung it from the bomb bay of a B-29 Superfortress. So they took off with this airplane, and they got it to a certain height, and then they dropped the Bell X-1, and so it started to glide, and then that's when the Bell X-1 would flip on its rocket engines to try to break the sound barrier. And that was the Bell X-1, and that was their attempt to break the sound barrier. Well, the gentleman that was successful in doing it on October 14th, 1947, was Chuck Yeager. And Chuck Yeager was the pilot of this airplane, and on October 14th, 1947, his airplane, the Bell X-1, dropped from the B-29 and basically at a certain point broke the sound barrier. And when you break the sound barrier, if you take a look at this picture here, you break the sound barrier. It is a modern jet, but you break the sound barrier and you actually cause a shock wave and a sonic boom. Okay, because this, what happens is the waves of the air now collide with each other and make this boom. So as you can see here, and you can kind of see three cones. Okay, so this cone looks like it's coming off the vertical and the tail of the airplane. This cone looks like it's coming off the wing of the airplane, and this cone you can see is coming off the canopy of the airplane. So this is at the point it's breaking the sound barrier. Now, this is caused because of condensed moisture in the air. So this is what they call a vapor cone. This doesn't necessarily happen every time you break the sound barrier. It's only when there's a lot of moisture in the air, and then you can get that vapor cone, because obviously the plane is heated up a little bit from going that fast. So now you basically are vaporizing that moisture in the air, and that's what you get. The one thing too is, a lot of people assume that when you break the sound barrier, it is one constant, or it's one sonic boom. As soon as you break that, as soon as you make 761 miles per hour, there's a sonic boom. But that is untrue. Once you break the sound barrier, you are consistently making sonic booms throughout the whole time you are above that speed. So that's why most flights that are going above the sound barrier are going Mach 1 is what they call it, hence the reason Ernest Mach you may have heard of. Most airplanes flying Mach 1 or above are not allowed to fly over populated areas or heavily or densely dense areas because it is constantly making sonic booms on the ground and disturbing what's on the ground, busting windows, things like that, depending on their altitude and things like that. So the sonic boom is one constant boom that follows the airplane all the way along. There is a video that comes right here, and this is another way that we had broke the sound barrier, and did not realize it at an early time in our span of aviation and a span of life in general. But there's a PowerPoint, and I want you to pause it here and watch how does a whip break the sound barrier, because a whip does break the sound barrier every time you crack a whip. And then after you get back from that, I'm just going to show you a little clip of the Chuck Yeager. It's from the movie The Right Stuff, and it's a movie. It's all fictitious, or I shouldn't say fictitious. They take some liberties and license with the movie as to how he breaks the sound barrier, but it's the movie part of it. And one of the things that I want to point out to you before you get into that other clip about the Chuck Yeager one is that the one gentleman hands him a stick, and supposedly, I don't know how true or how not true it is, but he hands him a stick because in the movie the night before he falls off his horse, breaks his ribs. He doesn't want to tell the Air Force he breaks his ribs because then that's going to prevent him from getting in the airplane to break the sound barrier. So this stick supposedly is going to help him get in there and close and lock the door, and so he doesn't have to tell. Again, is that true? Is it not true? I haven't read up enough to know for sure, but that's what the movie's going to show you. So when you watch that little 4-minute clip about Chuck Yeager breaking the sound barrier, you're going to see that, and that's what it's about. I just wanted to explain that to you. So at this point, pause the PowerPoint to watch how does a whip break. It's about a 11 or 12-minute video, and then you come back and then you watch the Chuck Yeager video. Okay, the Chuck Yeager video starts right here. So at that point, the sound barrier was broke with that one sonic boom that you heard in the video, and part of the thing is they weren't 100% sure on that. So then they heard that, they've heard it before, and that was the actual airplanes crashing in the past. So they assumed that he had crashed with that. So that was kind of, like I said, the Hollywood version. So take that with a grain of salt as to what actually happened, but it did happen in a general sense, just like that. Okay, so now we want to talk about airfoil, and the airfoil, the wings, and how the wing is shaped, all comes about based on how the air acts with the airplane, the machine. So airfoil design is really, really important part of an airplane, obviously. And the structure has a curved surface here, so you can see we got the upper camber, we got a lower camber, okay, trailing edge of the wing, the leading edge of the wing, and then the cord basically connects the leading edge to the trailing edge, and then the mean camber is basically like halfway between the curve that's halfway between. So when you design a wing, you want to get the best camber ratio. You want to get the best wing, and this is for your wing, this is for your rudder, this is for your elevators, your horizontal stabilizers. Everything needs to have a really good shape to keep the airplane aloft, so to keep that consistent lift that the early pioneers were looking for. So again, we talked about that with the leading edge. This is the thing that part that first meets the wind, okay? And this is the shape of the leading edge depends on what you're doing. If you want a high speed, you're going to have a very sharp leading edge. Remember I said earlier that you're going to have some turbulence when the wind hits that. If it's a little fatter, rounder, you're going to have more turbulence. If it's more sharp, you're going to have less. If you're trying to go faster, you want less turbulence up front. Okay, so you have that sharpening edge. If you're going to be a lower speed, you want more rounded, thicker. It gives you that more lift, more stability. Very similar to how the observation airplanes in World War I were having. So again, here's that. This is the leading edge we're talking about. And again, the skinnier it is, okay, like this here is more of a fat one. This is probably more of a lower speed airplane. So you're talking like 747 is really technically a lower speed airplane. The Cessna, small airplanes that you fly at the local airport, stuff like that. High speed airplanes, you're looking at fighter jets, and you're looking at those types of things right here, okay, with a much skinnier leading edge. When we move on, we talk about the camber. Again, that's immediately behind the leading edge. You have an upper and you have a lower camber, and the curve of that camber determines how thick that whole wing is, or that whole airfoil is. Positive camber obviously curves away from the center line. So if we had that center line, that chord type of thing that was in there, if it curves away from the chord, you have positive camber. Okay, and you can kind of see the center line would be from here to the back. So it curves away, and both of these are positive cambered, up and upper camber and the lower camber. So they're both curved away. And then you have a negative camber, where you have this one's curved away and this one's curved towards. So your center line is curved in towards it, just like that from the bottom. So you have two types of curvatures. Again, give you two different types of lift, different ways of maneuverability and stuff like that. Continue on with the trailing edge. This is the back part of the air wing or the airfoil. And this is where the upper and the lower cambers meet again. So they are together at the front, and then they meet again at the rear of the airfoil. And this is where basically the airstream here. So this is the airstream. The blue is the airstream, and this is where it meets again back here. And it doesn't necessarily meet right here. It may meet farther back. And again, this is all dependent on what angle your airfoil is at. If it's more at a level angle, it's going to meet at a cleaner spot, a little higher. If it's pitched more like this, it's going to meet at a different place, and so on and so forth. So the trailing edge right here, this is where the air ends up meeting up again, right back here at the trailing edge. And this is also where you're going to find some turbulence coming in here, depending on the shape of the wing and the angle of the wing and stuff like that. The chord is the imaginary line that connects the leading edge with the trailing edge. We kind of pointed that out to you. And it's used in explaining the angle of attack. So angle of attack is what angle the wing is at to how the plane is. If your plane is going forward and you want to climb, your angle of attack, your wing has to go upwards, and then you can climb. If you're going to want to descend, your angle of attack has to drop below the level line and descend then. Okay. Relative wind is opposite the flight path of the airfoil. So basically your relative wind is the wind that is coming at you. Okay, because your airplane is going forward, you are creating wind coming at you. It doesn't mean that if you're standing on the ground and the wind is blowing from south to north, okay, that's not relative wind. If you're flying from east to west, your relative wind is from the west, because you're flying into that wind that you're making to hit the airplane. That's what the relative wind is. Okay. Angle of attack, again, I just kind of said the angle between the chord and the relative wind. So as you're flying straight, how is your chord, that point between the leading edge and the trailing edge, how is that chord angled? Is it angled up so you're climbing it, or is it angled down so you're descending? And this is kind of a good example of that. So the relative wind is coming forward. Whoops, back up. Okay, the relative wind is coming forward, and this is your chord line, this green one. And if it's up like this, your airplane is climbing. If this green chord is exactly level you're in constant level flight. And if this green chord is angled downwards, that means you are descending. So in this case, this relative wind rate here is represented with this red line. And this here is your chord line, so your angle of attack is whatever angle this is. So climbing, your angle of attack could also be a negative angle of attack coming down, or a zero angle of attack. You're just flying straight and level. Okay. So that kind of gives you some idea about kind of how the airfoil works with the wind and works to keep some aloft. Again, I'm not going into anything really in a lot of detail. This is some very basic stuff that we talk about. The next thing I want to talk about though is, who is Daniel Bernoulli? Okay, yeah, we have somebody in this one other than just Chuck Yeager here. Daniel Bernoulli was a Dutch-born physicist, and obviously he was born a while ago. 1700 to 1782 was his lifespan. And in 1738, he discovered a relationship between the pressure and the speeds of fluids in motion. Okay, he found that as the velocity of a fluid increases, the pressure decreases. So it means as the air is flowing past a wing, okay, as air is flowing past a wing, it is going to go faster. And I want to back up here just to show you the airfoil again. So let's just say this, okay, if my wind, and we're going to use this at an angle, the relative wind is coming straight at this, right down the chord line, okay? When my air goes above the wing, okay, it has to go faster above the wing because I have more area to cover from here to here than if I have to go from here to here. So my air above the wing goes much faster than it does below the wing. So if it's going faster up here at a faster velocity up here, that means the pressure is lower up here, which allows it. Remember, we talked about pressure at the beginning here, less air above it, which makes it easier to rise up. So the faster the air flows up here, that makes it easier to go upwards. That's why a lot of wings are shaped like that, to make that go faster. So let's get back to here. The next thing I want is another short video, and it really kind of explains Daniel Bernoulli's principles, and that's what this is actually called, the Bernoulli principle. And it explains his principle in maybe something a little bit more modern and other than aviation or airplane that you can maybe get from it. So this video is the amazing Bernoulli.
Good morning, class. I am the amazing Daniel Bernoulli. Today we are going to discuss my principle, the Bernoulli principle. Developed first with liquids, but scientists also found that it works very well with gases. I'm going to show you some examples of my principle in action today. What do you think will happen when I blow across this paper?
Well, you're blowing at the top, so it's probably just going to push the paper down.
So as you can see, the paper rose when I blew across the top of it. If I were to blow between these two papers, do you think they would be blown apart or blown together? Sally, what do you think is going to happen?
Oh no. I'm going to push them apart.
Now you can flow between them. As you can see, the papers came together as if they were clapping. What you have to remember is that when you have fast-moving air, it generates a zone of low pressure. When you have slow-moving air, it generates a zone of high pressure. So when I blew across the paper, what happened is that I generated a zone of low pressure, causing the paper to rise from a high pressure zone to a low pressure zone. Today we see scientists that are generating new and wonderful wings on planes and gliders that help generate lift more effectively.
Bernoulli's principle helps explain why an aircraft can achieve lift because of the shape of its wings. They are shaped so that air flows faster over the top of the wing and slower underneath. The high air pressure underneath the wings will push the aircraft up into the lower air pressure zone above the wings. Bernoulli's discovery led to the first workable glider in 1853, invented by Sir George Cayley, and the Wright brothers' first plane in 1903. This principle is still important in flight today.
Now I'm going to show you my principle again, but in a new and wonderful way, using just a hair dryer and a ping pong ball. Are you ready? Look at it float! Oh! Isn't it amazing? Oh. Now for a variation on my hair dryer experiment. Watch what happens when I place the toilet paper tube over top the hair dryer. The tube acts as a funnel, creating a low pressure zone within the tube, forcing the ball upwards.
The air is moving fastest right above the hairdryer, creating a zone of low pressure. On either side of the fast-moving stream of air are zones of high pressure. The additional pressure acts as a barrier, keeping the ball in the zone of low pressure. When you tilt the hairdryer, the ball doesn't fall because it wants to stay in the low pressure zone.
So today, class, we discussed the Bernoulli principle, my main principle that says that fast-moving air creates a zone of low pressure, and slow-moving air creates a zone of high pressure. We saw this first when I blew across the paper. The paper moved from a zone of high pressure to a zone of low pressure. We also saw this when I blew between the pieces of paper, creating a zone of low pressure into which the two pieces of paper moved into. And finally, we used the hairdryer to generate a zone of low pressure into which the ping pong ball floated. And that is the amazing Bernoulli principle. I hope you enjoyed my lesson. Isn't it amazing? Yeah.
Okay, so that was kind of a demonstration on the Bernoulli principle and how the fast-moving air creates that low pressure, which then allows the ball to stay into the stream of air and stuff like that. And it kind of talks about how it works with an airplane. So this was our talking about the realm of flight. And we will continue on with our next version, talking about forces of flight in the next video.